why is it true that, you know, say that u is greater than v is greater than 0 implies square root of u is greater than the square root of v. Can anyone prove that immediately? Seems pretty obvious, you know, with you do a couple of number calculations. 0.8 is bigger than 0.7, and 0.64 is bigger than 0.49. Yeah, it seems to work between 0 and 1. And, you know, 3 is greater than 2, 3, square root of 3 is greater than square root of 2. It seems to work greater than 1. How about a proof? Simple.
It's obvious to me.
Obvious. Intuitively obvious to the most casual observer. That. Right. Well, let's see. If this is true, right, then this is true, which means that this, is true, right? That's just u minus v is greater than 0. Okay. Factor this. If u and v are both greater than 0, how is this positive or negative, this term here? Positive. Divide by that. It's not 0 and it's positive. So square root of u minus the square root of v is greater than 0, which means square root of u is greater than square root of v. Okay? All right. So those are some preliminaries. We're going to use the triangle inequality over and over again. So there is a proof of it, and we just went the nth degree there, so to speak, to show that the triangle inequality is true. A real kind of inelegant way to prove the triangle inequality is to consider the 4 cases. You know, obviously, one of these is 0. It's easy. But you consider the 4 cases: x greater than 0, y greater than 0, x. You know, you can do that. But this is the thing. Paul Erdős had a concept of the book proof is if God, I don't think he was a theist, but if God were writing out all the proofs to the mathematical theorems, God would not do the 4 cases. He would use something.
This term for God, I think, was
the supreme fashion. Well, there you go. Apparently he was, no. Probably not a good Catholic theory, I'll tell you that. All right. Bolzano-Weierstrass. Bolzano was not Italian, but he was a Czech. And the Bolzano-Weierstrass theorem is this. We're always talking about the real numbers here. If S is a set of real numbers and cardinality of S is infinite. And S is sitting in an interval, closed interval, in other words, it's bounded, then S has a limit or accumulation. I call this the you can run but you can't hide proof. You know, just think, oh, here's another inappropriate analogy, I guess. In Pittsburgh, if you, there's an expression, you try to put too much in a container, it's a living, you know what living is? Sounds like it's some kind of Hungarian word, living. That's 5 pounds of crap in a 2-pound bag. So it's overstuffed. It's
Use 10 and 5.
overstuffed, 10 and 5. Yeah, you get any 2 levels there. It's too much stuff. Well, the content, the intuitive content of the Bolzano, see now you'll remember this, the intuitive content of the Bolzano-Weierstrass theory is this. If you have a bounded set of infinite numbers, there must be some real number. Not necessarily in the set, but real close to it. Could be in the set. But there will be a real number which is close to infinitely many members of the set S. You can't stay away, right? You can jump around. You can say, all right, I'm in this bounded set alpha beta, and I have to put an infinite number of letters in sort of a bounded, that's another, postal boxes, right? So I start putting the letters in. And for a while there, it seems like I can do it. But then I say, well, 1 over n isn't good enough. Maybe 1 over n squared, we'll try that. And we just keep going, and we find, geez, no matter what we do, we are stuck placing an infinite number of points in S arbitrarily close to some point in the closed interval, actually, alpha beta. If S itself happens to be closed, then that limit point is a part of S, and we would say that S is Bolzano-Weierstrass compact. The closed bounded infinite set of real numbers is Bolzano-Weierstrass compact. There are different forms of compactness. There are 4 of them that I can think of at the moment. There's Bolzano-Weierstrass compactness, countable compactness, sequential compactness, and ordinary compactness. When we get to those, I'll clarify. But this property we're looking at here, oh, by the way, in the real numbers, all 4 concepts coalesce. So if a set of numbers is one of those types of compactness, it's all the others. But there are spaces where all 4 ideas are different. That's why there are the 4 ideas. Okay? Right. So let's try to prove Bolzano-Weierstrass. We have a set that's infinite and is contained in a closed interval. Well, tell you what. It'll make life a whole lot easier if we're allowed to assume the nested interval theorem. If A n B n is a sequence of closed intervals inside R, such that an plus 1, en plus 1 is not outside of A and B n. There, you could go through a stretch of indices where they would sync, like you didn't get any smaller. But eventually, and the limit, as n goes to infinity, of, you could write it this way, the norm of an, bn, which of course is bn minus an, equals 0. Then, the intersection, n equals 1 to infinity, of these things is 1 point, lambda, which is common to them all. Obviously, we have to be common to them all since it's in their intersection. But it's not like there's a whole interval that's common to them all. You can see why that wouldn't happen. You can't have an interval common to them all because the length of these things is getting smaller and smaller. All you can tolerate is 1 point. The possibility exists that that point isn't even there, and you could go squeezing this thing down and poof, there's nothing, you know, it could be the null set. All right, let's prove this, and then Bolzano-Weierstrass won't be too hard. Any ideas on proof? Any intuitive? Well, drawing a picture is always good.
Tom,
Yes.
I'm sorry. That last variable, is that A to B?
A sub n, comma, B sub n.
Sorry.
Right, this is the norm of it, and that's the intersection of represented. Okay.